Okay, this next section deals with equipotential surfaces and electron volts. Now, basically this is a continuation of Coulomb's law, which says that there's an inverse relationship between the force of attraction or repulsion between electrons and the distance squared. Okay, but the bottom line is that while it is a truly ever-present substance, electricity is, and the attraction repulsion of like or unlike charges, the representation of them is man-made. And I want to be very clear on that. You're never going to see lines of electricity coming off the surface. But there is going to be forces, and those forces are represented by lines for that very reason. So like if we take a surface like this right here, we have a charge here and a surface that is charged up, and we have radiation of particles coming, not particles, but forces coming off of this. If we were to get farther away from this, like so, the new point that I've shown here, where this is the original right here, and this is the new one right here, if we took a look at every point, measured the electric field, shall we say, also could say the amount of force coming off at those points is going to be weaker than what was right here, but these are all going to be equal. If you have a weird shaped one, you're going to get a larger weird shape configuration around that, because the distance away from each point of contact at the tangent with the surface of this object here is going to be the same. And the weird shaped ones do as well. Now, because we're dealing with such small charges, we have to come up with a new measurement. I mean, we could use joules and the extremely low powers of 10, 10 to the negative 19, 10 to the negative 18, or whatever it is we're dealing with, or we can reconstruct a measurement so that it's not so small. And so scientists went to something called an electron volt. An electron volt is simply, it's a value of work or energy. It could be kinetic energy, it could be potential energy. But the definition, as you see from EV, E is the charge of electron, and they use electron volt, it could be proton as well, times 1 volt. And we know that the charge of electron is 1.60 times 10 to the negative 19 coulombs. We also know that 1 volt has been defined as 1 joule per coulomb, so the coulombs cancel out. And our electron volt value, like I said, which is a measurement of energy, is 1.60 times 10 to the negative 19 joules for every 1 electron volt. So rather than throw these numbers out there, they use a representation that's a little more palatable, shall we say, a little more agreeable, a lot more easily understood, particularly by those who don't really understand what an electron volt is. It's a number that they can deal with. Kind of like what we do with pH and magnitude of earthquakes or anything that we change the numbering system so that the general public can get a better handle on it. The first example I gave you here was, let's suppose you have 150 kilo electron volts. I want to know how many electron volts that is and how many joules that is based upon what we talked about. Okay, well, the prefix kilo, the nice thing about the SI system is no matter what base unit you use, meter, second, liter, blah, 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 electron volts, it still means 1,000. So 1,000 electron volts is equivalent to 1 kilo electron volt. And so we get 1.50 times 10 to the 5th electron volts. Now that's important in being able to figure out how much work is actually being done under those conditions if at the microscopic or electronic scale. And so we take that 1.50 times 10 to the 5th electron volts and define how many joules that is. We just did that in the previous page. The equivalency is 1.60 times 10 to the negative 19 joules for every 1 electron volt. And we get 2.40 times 10 to the negative 14 joules is what represents that. Okay, so that's just basic conversion problems. The next one, we're given a distance of a charge that is 65.0 centimeters away from the electric force strength. And so the question is, what is the voltage when it's 65 centimeters away from one of the plates of our electric field? So the formula for this is, I could put the vector sign there, but we understand that this is not energy. We understand that this is electric field, which is found by taking the voltage and divided by, or the potential rather, and divided by the distance. So we're given the electronic field as 3,000 volts per meter. That is equal to volts over the distance, so we had to change the centimeters to meters. We get 0.650 meters. And as any Algebra 1 student can tell you, you get V by itself and multiply both sides by 0.650 meters. And we get 1,950 volts. Okay, the third example we had here is we're given a mass of a proton, and the kinetic energy of that proton is 3.75 mega electron volts. And the question is, what is the velocity that it is at in order to maintain that kinetic energy? And since kinetic energy is defined as 1/2 mv squared, going back to way back when we talked about energy, we have to change the mega electron volts over to electron volts over to joules. So the kinetic energy turns out to be 6.00 times 10 to the negative 13 joules when we multiply all that garbage together. And that's going to equal to 1/2 the mass, which is the mass of the proton, times its velocity squared. And again, the basic algebra problem, clear out this stuff over here, bring it over here by dividing by those two quantities. We get a V squared of 7.18 times 10 to the 14th meters squared per second squared. Take the square root of both sides, get 2.68 times 10 to the 7 meters per second. Very, very fast, but not fast as speed of light, thank goodness, because that couldn't happen. So let's take a look at the practice problems that's related to these. It's at the bottom of your script. There are 5 again, just like I always do. And somehow, all right, there it is. And there's our 5 practice problems. Have fun.